students, let us continue with the chapter Real Numbers. In this episode, we shall learn about rational numbers and their decimal expansions. So students, we know we have already studied that rational numbers have either a terminating decimal expansion or a non-terminating repeating decimal expansion. Here we are going to consider a rational number, say p upon q, where q is not equal to 0, and explore exactly when the decimal expansion of p upon q is terminating and when it is non-terminating, repeating or recurring. Here, let us look into this theorem. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p upon q, where p and q are co-prime, and the prime factorization of q is of the form 2 to the power n into 5 to the power m, where n and m are non-negative integers. Let us look into another theorem. Let x is equal to p upon q be rational number such that the prime factorization of q is of the form 2 to the power n into 5 to the power m, where n and m are non-negative integers. Then x has a decimal expansion which terminates. We have another important theorem here which states that let x is equal to p upon q be a rational number such that the prime factorization of q is not of the form 2 to the power n into 5 to the power m, where n and m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating, that is recurring. So, we can conclude that the decimal expansion of every rational number is either terminating or non-terminating, repeating. Always remember that if the denominator has only factors of 2 and 5, or if it is of the form 2 to the power n into 5 to the power m, then it has terminating decimal expansion. And if the denominator has factors other than 2 and 5, then it has a non-terminating decimal expansion. I hope it is clear. Now, let us start with the exercise 1.4. Here, the question number 1 says, without performing the long division, state whether the following rational numbers will have a terminating decimal expansion or a non-terminating repeating decimal expansion. Question is 13 upon 3125. Let us factorize the denominator. We get 3125 as 5 into 5 into 5 into 5 into 5. That means 5 to the power 5. Then, since the denominator has only 5 as its factor, therefore, 13 upon 3125 has a terminating decimal expansion. Let us see the second part, which is 17 upon 8. Factorizing the denominator, we are keeping in mind the theorem. Okay. So, we are factorizing the denominator. We get 8 as 2 into 2 into 2, that is 2 to the power 3. Since the denominator has only 2 as its factor, 17 upon 8 has a terminating decimal expansion. I hope it is clear. Next part is 64 divided by 455. Factorizing the denominator, we get 455 as 5 into 7 into 13. Since the denominator is not in the form of 2 to the power n into 5 to the power m, thus 64 upon 455 has a non-terminating decimal expansion. Next question is 15 divided by 1600. Here, factorizing the denominator, we get 1600 as 2 to the power 6 into 5 to the power 2. Since the denominator is in the form 2 to the power n into 5 to the power m, thus 15 upon 1600 has a terminating decimal expansion. Let us see the next part. 29 divided by 343. Factorizing the denominator, we get 343 as 7 into 7 into 7, that is 7 power 3. We can see here, since the denominator is not in the form of 2 to the power n into 5 to the power m, thus 29 divided by 343 has a non-terminating decimal expansion. Let us see the next one. It is 23 divided by 2 to the power 3 into 5 to the power 2. Already the factors are done for us in this question. What do we notice? Clearly, the denominator is in the form 2 to the power n into 5 to the power m. Hence, 23 divided by 2 to the power 3, 5 to the power 2 has a terminating decimal expansion. Next, 129 divided by 2 to the power 2, 5 to the power 7 and 7 to the power 5. What do we notice here? 7 is extra for us, we do not want according to our theorem, right. So, clearly the denominator is not in the form 2 to the power n into 5 to the power m. Therefore, 129 divided by 2 to the power 2, 5 to the power 7 into 7 to the power 5 has a non-terminating decimal expansion. I hope it is clear. Let us see the next part. 6 upon 15. We need to find factors of numerator also here, because common factors will be cancelled in numerator and denominator. Look, 15 can be written as 3 into 5, whereas 6 can be written as 3 into 2. 3 being common factor, I can cancel out, and what do we have in the denominator then? The denominator has only 5 as its factor, thus 6 upon 15 has a terminating decimal expansion. So, students, let us look into the next question here, which says, write down the decimal expansions of those rational numbers in question above which have terminating decimal expansion. Okay. So, one method is just by division we can find out the decimal expansion. Let us have another method which is more simpler. What we will be doing in this? We will try to get the denominator in powers of 10. How do we do that? Let me take 13 upon 3125. We have seen that the factors were 5 to the power 6, 3125, we had 5 6s, 5 2s and 5 1s, again with 5 2s and 5 5s. No, I am sorry, it is 5 to the power 5. We had 5 to the power 5. Now, I told you we will try to convert the denominator as powers of 10. So, if I multiply and divide by 2 to the power 5, I get the denominator as powers of 10. How? We have 13 into 2 to the power 5 is how much? 2 2s are 4, 4 2s are 8, 8 2s are 16, 16 2s are 32 upon 5 into 2 power 5, or we get 32 multiplied by 13 . Yes, it is 416 in the numerator, and denominator I get 10 to the power 5, which can be written as 416 upon 1 followed by 5 zeros. It is easy to express now in the form of decimals. You have 2 zeros and 416. So, this is the decimal expansion of 13 upon 3125. I hope it is clear. Let us do the next part. We have 17 upon 8. Now, what are the factors of the denominator 8? Obviously, 2 to the power 3. We have to convert the denominator as powers of 10. So, we multiply and divide by 5 to the power 3. What do we get? It is 17 into 125. 5 into 5 into 5 is 125, and denominator is obviously 2 into 5 power 3, which can be written as 125. I will multiply by 17, it gives me 7 5s are 35 and 875. 5 to 1, I get, yes, 2125. So, 2125 upon 10 power 3, which can easily be written as 2125 divided by 1 followed by 3 zeros. Now, I can express this as 2.125. This is the decimal expansion of 17 upon 8. I hope it is clear. Now, let us go to the next part. We have 15 divided by 1600. Now, 1600, let us find factors. We have to find all the prime factors. We get 1, 2, 3, 4, 5, 6. So, it is 2 power 6 into 5 power 2. So, our approach is to make the denominator as power of 10. How can we do that? We can take this as 2 to the power 6 into 5 to the power 2. Let us multiply and divide by 5 power 4. So, 15 into, this is 5 5s are 25, 25 into 25 gives me 625, and denominator is 2 to the power 6 into 5 power 6, which can be simplified as 5 2s are 10 and 2 gives me 31, 5 2 6. So, 9375 is the numerator upon 10 power 6. That means 9375 divided by 1 followed by 6 zeros, which can be written as 0.009375. So, students, I hope you have understood this method. Now, let us see the next part. Here in this question, we have 23 upon 2 to the power 3 into 5 to the power 2. So, the factors are already done for us, 2 to the power 3 into 5 power 2. In order to get power of 10, I need to just multiply and divide by 5 power 1. Okay. So, 23 into 5 upon 2 to the power 3 into 5 to the power 3, which can be written as 115 upon 10 power 3. We are using laws of exponents. So, 115 upon 1 followed by 3 zeros, that gives us 0.115. I hope the method is clear. It is easy. So, students, let us do the next part. It is 35 divided by 50. What are the factors of 35? Yes, you are right, 7 5s are 35, and here I can get 5 into 5 into 2. Okay. So, 1 5 gets cancelled, I get 7 upon 10. Fantastic. I need not change. So, it is 0.7 is the decimal expansion of 35 upon 50. Let us do the next part now. So, students, let us look into the next question, which says the following real numbers have decimal expansions as given below. In each case, decide whether they are rational or not. If they are rational and of the form P upon Q, what can you say about the prime factors of Q? First question is 43.12345678 Since this number has a terminating decimal expansion, it is a rational number of the form P upon Q, and Q is of the form 2 to the power n into 5 to the power m. That is, the prime factors of Q will be either 2 or 5 or both. Now, let us see the next part. It is 0.120, 1200, 12000, 12000. The decimal expansion is neither terminating nor recurring. Therefore, the given number is an irrational number. So, let us see the next part. We have 43.12345678 with a bar. Okay. Since the decimal expansion is non-terminating, recurring, the given number is a rational number of the form P upon Q, and Q is not of the form 2 to the power n into 5 to the power m. That is, the prime factors of Q will also have a factor other than 2 or 5. I hope it is clear. Now, it is time to take assignment. We have question number 1. Without performing the long division, state whether the following rational numbers will have a terminating decimal expansion or non-terminating repeating decimal expansion. Part 1, 13 divided by 125. Second, 7 upon 80. Third, 100 divided by 700. So, students, in this episode, we learned how to express the rational numbers in the decimal expansion form. I hope you enjoyed the session. Please perform the assignment questions and you will be mastering the concept. Thank you.